Over the past decade, our research team has been engaged in a series of experimental archaeology projects aimed at reconstructing and testing Eneolithic ceramic kilns inspired by the Cucuteni-Trypillia culture. These experiments have provided valuable insights into the construction techniques, firing efficiency, and operational challenges of prehistoric kilns. Our efforts have led to the successful reconstructions and testing of the 3 outdoor kilns, each refining our understanding of ceramic technology in the late Eneolithic period. More recently, this accumulated knowledge has been applied to the construction of a full-scale museum kiln at the History Museum of Piatra Neamț, an indoor installation designed to bring our experimental findings to a wider audience. The present discussion focuses on the interactive process of building and using these kilns, drawing upon 3 major experimental projects and subsequent laboratory analyses that allow us to determine firing temperatures and assess ceramic properties post-experimentations. Additionally, we will explore how these experiments culminated in the creation of the museum kiln, which now serves as a tangible bridge between academic research and public engagement, offering visitors a direct experience of Eneolithic ceramic production techniques. The project began with the reconstruction of a late Cucuteni-Trypillia 2-chamber updraft kiln discovered at Stolniceni, Republic of Moldova. The archaeological find, exceptionally well preserved and meticulously documented, served as a crucial reference for understanding prehistoric firing technology. In September 27, a team of archaeologists undertook a full-scale reconstruction near the discovery site, closely following the original design and dimensions. The kiln layout featured a lower fire chamber, built with 2 combustion channels, and an upper chamber where the pottery was placed. Authentic materials were prioritized, local clay, water, and tempering fibers like chaff, where willow branches were used to form the dome structure. The excavation of the firing area and stocking pit was carefully conducted, followed by the construction of clay walls. The clay for the structure was prepared by mixing it with straw to enhance cohesion and thermal resistance. One of the major challenges encountered was the dome constructions. Archaeological evidence provided only limited information on how the original kiln's wall was shaped. Based on similar structures and ethnographic analysis, a wattle-and dome with a top vent was hypothesized. Willow roots were woven into a cradle, and the cob mixture of clay and chaff was gradually applied, were it to form a thick head retaining roof. The kiln was left to dry naturally for 2 days, aided by small kindling fires lit inside to accelerate the hardening process. The first experimental firing lasted over 10 hours, with a gradual increase in temperature to prevent thermal shock. Observers noted efficient heat circulation within the kiln, ensuring even exposure of the pottery to the flames. However, while the structure performed well, the maximum temperature reached only around 700 degrees Celsius, lower than anticipated. Laboratory analyses conducted on the fire ceramics, including X-ray diffraction and scanning electron microscopy, confirmed incomplete vitrification, suggesting that the adjustments were needed in kiln ventilation and fuel management. One key issue identified was the excessive width of the top opening, which allowed heat to escape instead of being retained. Additionally, the kiln's underloading may have prevented heat from building efficiently. Despite these setbacks, the experiment successfully demonstrated the general viability of the Cucuteni kiln design, while highlighting areas for refinement. Building on the Stolniceni trial, a second kiln was constructed at the Boiceni research base in 2020 to test modifications made at improving firing efficiency. The primary innovation was the addition of small vent holes positioned around the fire channels. As observed in some archaeology examples, researchers hypothesized that these openings would enhance airflow and promote a more uniform heat distribution. The kiln structure was similar to the first, but with a crucial adjustment. A wooden frame was used to support the dome, which was then covered in layers of clay. Additionally, the kiln was filled to full capacity with ceramic vessels, ensuring optimal heat absorption. This firing produces significantly better results, reaching temperatures of 850 to 900 degrees Celsius across most of the chamber. The modified airflow system operated to create a more efficient combustion process allowed for higher and more consistent temperatures. Post-experimental analysis confirmed that the higher temperatures were achieved across a wider range of the kiln interior. Further transformed infrared spectroscopy revealed that kaolin and fully transformed into moonlight, a sign of advanced sintering. Additionally, thermogravimetric analysis indicated a complete burnout of organic materials, suggesting an improved combustion process. These findings demonstrated that the kiln structural adaptation had a measurable impact on performance. The success of this firing reinforced the importance of kiln ventilation in prehistoric ceramic production. The results confirmed that Cucuteni potters were actively experimenting with design features to optimize heat efficiency, providing a compelling example of ancient technological ingenuity. However, research still sought to push firing temperatures by 900 degrees Celsius, prompting the planning of a third experiment. The final experiment in 2022 introduced two major refinements, replacing the wattle and daub dome with a daub brick structure and using high calorific hardware fuel. These changes were designed to enhance heat retention and ensure a steady fuel supply for sustained high temperatures. The firing process proceeded smoothly, achieving an immersive uniformity in temperature distributions. By the end of the session, internal temperatures reached 850 to 900 degrees Celsius throughout the kiln chamber. Producing fully vitrified ceramics, the improved design resulted in stronger, more durable pottery, closely matching archaeological specimens. These repeated experiments, presented at various conferences and published in academic journals, have contributed toward growing recognition within the Romanian archaeological community. As a result, in 2023 we received an official request from the History Museum of Piatra Neamț to construct a ceramic firing kiln inside the buildings, within one of the exhibition halls dedicated to the Chalcolithic Cucuteni culture. At the time, the museum was undergoing renovation, providing an opportunity to integrate these installations into the redesigned exhibition space. We agreed to the project under the condition that the kiln would be built using authentic materials, clay, wood, straw, and water, and full-scale dimensions, rather than being a scaled-down replica or a poor decorative installations made from artificial materials. The next step involved drafting a detailed project proposal, including various sketches of the kiln and inventory of required materials, estimated construction phases, and other logistical considerations. Our initial plan was to create a wooden framework that would be filled with remade clay, replicating the solid earthen foundation of the ancient kilns. Within this structure, we intended to carve out or preserve the underground elements of the kiln, such as the fire channels, the fuel feeding opening, and the stoker's pit, and then constructed the vaulted dome above it. The museum administration approved all our proposals, but the execution of the project was delayed by a year until September 2024 due to extended renovations work. However, our preparations began earlier. During the summer, at our archaeological research base, we reshaped, painted, and fired the ceramic vessels that would be displayed inside the kiln. For the firing process, we used the same kiln built in 2022, requiring only a thorough cleaning and the reconstructions of the upper part of the dome after placing the vessels inside. Additionally, based on our initial calculations, we prepared the wheel of framework on which the kiln's dome will be built along with the various accessories that will be displayed alongside the kiln, illustrating prehistoric pottery making techniques. These additions included a rotating modeling device used for shaping large vessels with a partially finished pot demonstrating the coil building technique, wooden stone tools used for shaping, smoothing, and burnishing ceramics, small vessels containing prepared pigments for painting, and brushes with clay or wooden handles made from animal hair and plant fibers. These elements aim to create a dynamic and immersive exhibit showcasing the tools and the techniques employed by Neolithic potters. The construction of the museum kiln took 2 weeks, but certain adjustments and exceptions had to be made to our self-imposed rule of using only prehistoric materials. The high humidity inside the museum, combined with the cold and the damp weather outside, forced us to abandon our initial plan of using a formwork file with the wet clay to stimulate the ground surface. Instead, we opted for a platform made of reclaimed bricks from a demolished structure. These bricks were bonded with clay and covered with an additional clay layer to maintain an authentic appearance. Another significant change was the abandonment of the willow framework initially intended for the kiln's dome. The architect in charge of the exhibition's layout relocated the kiln from its plain and central position to a corner between two walls. This shift made it impossible to construct the dome from the outside, as would have been standard practice in prehistoric conditions. As a result, we had to adapt our construction method to the constraints of the indoor space. A further challenge was the quality of the clay provided by the museum, which contained an excessive amount of sand, making it difficult to mold and structurally unstable. This required use to conduct field research around the city to locate a suitable clay source, securing over a ton of material necessary for the kiln's construction. As the dome constructions progressed, we also had to integrate LED lights with a flame effects inside the fire channels and the ceramic chamber, along with placing our experimental ceramic vessel inside the kiln. This step, originally planned for after the dome's completion, became necessary midway through the construction since the closed dome would have made such installation impossible. To enhance the kiln's realism, we applied mineral pigments to its surface, drawing on our outdoor firing experience to recreate the appearance of an active kiln in the midst of firings. In the stocking pit, we arranged a reconstructed rotating modeling device, presumed to have been used in prehistory, with a partially shaped vessel demonstrating the coiling technique. Nearby, we placed prepared clay for vessels modeling, along with the small containers of mineral oxides used for painting ceramics. The entire installation, completed by a short film looping NERPy, features archaeological footage of Cucuteni kilns from excavations and the scenes from our experimental firing. The goal is to offer visitors, regardless of their level of prior knowledge, a comprehensive and visually engaging insight into the chain operator of Cucuteni ceramic production. Through this setup, we aim to bridge academic research and public understanding, making the intricate process of Eneolithic pottery making accessible and immersive for all audience. Beyond its experimental value, it is kiln served as a prototype for an indoor exhibit at History Museum of Piatra Neamț. The museum kiln was designed to replicate the successful 2022 model, ensuring visitors can now see a life-size Cucuteni kiln, authentic in its structural features, configured as it would have functioned, providing an interactive educational experience. This installation bridged academic research with public engagement, allowing museum goers to explore the complexities of prehistoric ceramic production. The impact of this experimental archaeology project reached beyond academia and facing public engagement with prehistoric technologies. The kiln constructions and fire involved the students, museum visitors, and the community. The museum kiln at Piatra Neamț offers visitors a first-hand look at ancient pottery making with interactive features like stimulated firing and educational panels. By integrating real experimental data, the exhibit provides an immersive learning experience. The project also helped train the young archaeologists through hands-on participations in kiln constructions, fire, and ceramic analysis. Through public events and museum displays, it has made Eneolithic ceramic technology more accessible and engaging to a wider audience. The experimental kiln reconstructions in the project have greatly advanced the understanding of Cucuteni-Trypillia ceramic firing, its iterations refining aspects like airflow and the fuel efficiency, culminating in a museum installation that brings prehistoric pottery making to life. By blending scientific research with public engagement, this project bridges academia and cultural heritage education. The kiln do more than confirm historical theories. They spark curiosity and appreciation for ancient craftsmanship, making this knowledge accessible beyond the scholars. The reconstructed kiln at the History Museum of Piatra Neamț exemplifies this approach, turning research into an interactive experience that deepens the public's connections to the past.